All right. Good morning, everyone. Let's start. Do you have any questions before we start? Wow, that's a long question. Let's see here. Any chance push back a day or two? Yeah. Monday. Yeah, because we don't have class on Friday anyway. So yeah, I can push back to Monday, next Monday. That work? Cool. Yeah. Any other question? By the way, right, even though the homework's pushed back, that doesn't mean that the materials, right, are pushed back. It's still everything up to, right, the last Friday material, which are reflected through the homework, for example. So you're still responsible for the materials for the midterm. Yeah, good question too. I will do that. I actually I can do that with the past midterm. I can set up like a past midterm exam something, so you can go in and check it out. Yeah. Mhm. Anything else? Today's quiz is not pushed back. The homework, which is due on Friday, is pushed back to Monday. Right, Christine? I understand you right. Yeah, talking about the homework, not the. Cramer lower bound, and moving on to conference. No, we're not doing reviewing. Oh shoot, sorry, I forgot to ask the TA. The TA is supposed to hold a review session for you. Did he say anything about that? Okay. I'll shoot him an email. Okay, cool. Yep, we'll try to. What are you asking, Alice? I see. Actually now I recognize. I think I meant 1A to 1F. I don't know why I say 1E, 1F. That's weird, right? It should be 1A to 1F. But anyway, well, I already said what it is. So yeah, use the previous part to do E and F. I think I meant 1A to 1F. I don't know why I typed 1E to 1F. 1A to 1F. But okay, just do E and F then. But you can use the results without doing it on the quiz. Okay. All good. All right. So yeah, set up the MT exam, not, well, whatever, pass exam for you to check out. Tell the TA to hold you the review sessions and push the exam back. All right, I'll do those. Okay. So let's start the lecture then. So we're still somewhere in 10.3, but it's a very special topic in 10.3 called Cramér lower bound. So the question is this, right? That basically, suppose you have x1 up to xn, IID, and with some dependence on with population distribution depending on theta. Okay, some unknown parameter theta. You have theta hat, right, as a parameter for theta, as an estimator for theta. And actually, theta hat is not the only estimator for theta. You could have, right, many theta hats, more than one. Okay, and so obviously in the empty context of not stating much, then you want to choose the theta hat, right, that has the best MSE, right? Overall, we probably want to choose the theta hat that minimizes the MSE. The mean square error, okay? Whichever like estimator that would make this quantity minimum will be your best choice. But well, trust me on this, is not well, I mean, I don't have time to come up with like an example, but the procedure to minimize the MSE in general, right? Actually, you will see that even without minimizing the MSE in general, this is a hard process, or at least a complicated process, okay? So not simple. Let me just say this, right? Not simple in general to do in general. And as you see, even when we simplify, the question is still not simple. So right, so all I want to say here is mean square error is the target in general, okay? In other words, both the bias and the variance, some of them, you want to minimize them. But so what we try to do now is to assume that bias is 0. So we simplify, right? We specialize to, we kind of like, simplify to the class of unbiased estimators. Okay. So in other words, what we assume, right, is that expectation of theta hat is equal to theta. All right. And what we want is, so obviously, right, in the case of the unbiased estimators, then the mean square error would just be the variance, because the bias is equal to 0. So then among, right, so now the question is, among the, right, unbiased estimators, can we pick the one with minimum variance, or the most efficient one, right, if you will? So you see, the theme is still mean square error in general, right? But because mean square error includes both bias and variance, it's hard to do in general. So we just we specialize to only variance, assuming, right, no bias. But even that, as you see, is not an easy question to answer in general. So because the question is, how do you know? how do you know that you have reached the minimum variance? Okay. So actually, right, how do we know? The difficult question is, how do we know that we cannot do better? By do better, I mean come up with something else that has smaller variance. Okay. For example, let's say you have x1 up to xn, IID, right, with mean mu, variance sigma square. All right. X bar, right, is our routine mu hat. Okay. So we know X bar is unbiased. We know variance of X bar is sigma square over n. All right. But in the context of this question, right, is there any other mu hat out there that's still unbiased, but has smaller variance than X bar? Okay. So that's what I mean by how do we know that we cannot do better? Or is the same thing. How do we know that this may be it? This may be the best that we can do. Okay. Because, you know, the difficulty is that our mind, right, cannot conceive of all possible estimators. That's simply impossible, right? Because how do you say that this is the only ways to estimate mu, right? Because estimators by definition doesn't have any restriction to it. So without, right, some bound, right, without some bound that tells us that we have achieved something absolutely minimum, then it's hard for us to tell. So that's what Cramér-Rao lower bound does. Cramér-Rao lower bound gives us, right, a criterion to tell, right, when we have possibly achieved the best, meaning the minimum variance. Okay. So the Cramér-Rao lower bound goes as follows. It's actually a theorem. It says that if theta hat, okay, is unbiased for theta, then variance of theta hat will always be no less than 1 over n expectation of the derivative with respect to theta of the log of the density or the probability function with respect to this square, like that. Okay. So if you have not seen this before, then this will be a strange and maybe scary object. All right. So let me first say, right, where this, okay, is the population density or probability distribution function. Okay. So anyway, right, that's probably not helping too much. So, I mean, in the sense that kind of bring out what this means. But first of all, right, on the more abstract level, let me just say that don't worry about this. What is this to begin with? Look at the message of a Khmer round. Okay, Khmer round tells you that if you have any unbiased estimator, then its variance is automatically bounded by something that's pretty universal. What do I mean by universal? Universal means it doesn't depend on how you construct this guy, right? That's the core and the coolness of Khmer round, if you will, right? Whatever this is, don't worry about it yet, but pay attention to whatever that it depends on, right? Some derivative, some population information, but it does not depend in any way on how you construct this theta hat. And that's why it's universal, because it says, I don't care how you construct this guy, this is a lower bound for this population. As long as you sample from this population, this is a lower bound. So, okay, what is the implication of this message to the question that we're asking? The implication is like this, right? Here, I did not say more about the population, right? To use Khmer round, you need more information. In other words, the density or the probability. But if you go ahead and plug that information in and found whatever it is, and suppose that by a stroke of luck is exactly this, okay? If by a stroke of luck, Khmer round lower bound is exactly this, then, by calculation, then what did you get? Then what you got is that basically, then X bar is the best, okay, is the best. Why? Because, right, nothing else can be lower than that by this result, okay? So that's how it's used. In other words, if you have found an unbiased estimator that has reached the Khmer round lower bound, then is a best, rather, right? Not the best, maybe, because there could be some other ones that maybe also achieve the same bound. Who knows? But is the one of the best. And so we'll just say the best. All right. So let me put that right down. So if, right, we have an estimated theta hat, right, that is unbiased, and right, and the variance and the variance of theta hat is equal to the Khmer round bound, then theta hat is called a UMVE. Unbiased minimum variance estimator. Okay, unbiased minimum variance estimator. All right, UMVE. I mean, fancy name. All right, for theta, of course. So that's the use. All right. Now, so on the other hand, right, pay attention to this. Suppose we have a theta hat, right? Of course, unbiased, that does not, right, achieve the Khmer round bound. Okay. So, basically what that means is this is strictly bigger. It says that it's no, so it doesn't say much. It doesn't say much. That's the unfortunate message. Because, right, it says that it's the best MSE among the unbiased estimators because it's a variance. But if you allow biasness, then you may get better. You may do better than the Khmer round. Okay, that actually is a tricky part. So that that is not yeah, that doesn't say anything about MSE in general. If you allow biasness, you may be able to do better. Yeah, exactly. That's the tricky part. Of course, you can do more work, right? Based on this foundation and go back to the original question, you could combine them with the analysis of biasness and do better. So if your interest is in the MSE, then right, that's why I say we just have to be willing to look into the not so simple work and see what's going on there. Yeah, but of course, if you achieve the Khmer bound, that doesn't say that you're the best in MSE yet. So my question is this, right? Suppose you have a theta hat that's unbiased, that does not achieve the bound. Okay, so that means that this is strictly bigger. Does this mean that theta hat is not a UMV? If you have an unbiased estimator, right? Somehow if the Khmer bound is not achieved, does that mean that this is not a UMV? Meaning it's not the uniform minimum variance estimator. Sorry, unbiased, not uniform, unbiased minimum variance estimator. What do you think? Mm-hmm. Let me restart my iPad real quick, okay? Actually, Derek is right in the sense of this, that the negative of this is not clear. In other words, right, the Khmer round just say that any unbiased estimator must be bigger and equal to this. But it never says that you must have something that achieves it. You see, it never says that there is something. No, it's fine. It's a subtle concept, right? For example, I mean, it's really a easy example, but the logic is clear. Suppose I have a function, right? That let's say the minimum is at 1. Then this is f of x. Then it's still fine for me to say f of x is bigger than or equal to 0, right? There's nothing wrong in that. Agree? But then let's say here at 2. Is 2 the minimum of f? Absolutely. But is f of 2 equal to 0, bigger equal to 0? No, right? So in this sense, right, the Khmer bound serves as more of a positive statement rather than a negative statement. In other words, right, when you test the Khmer bound, you really want to pray for that stroke of good luck. In other words, if you achieve it, then you know, yes, it's the best. But if you do not achieve it, then we don't know. Then you don't know. Is that okay? It may be the best. It may be the best. It's just we don't know. Is that okay? So, right. So do keep that in mind, that the logic works that way. On the other hand, right, realistically, empirically, I think a lot of estimators kind of get close to the Khmer bound, if not equal to it. So in other words, it serves as a pretty good bound that most reasonable estimators should be close to it anyway, or equal to it. Okay, but yeah. So but when you work with the logic, just keep in mind that just because you're not equal to amount doesn't mean that you're not it. Okay. Any question here? Okay. So the next idea in the next thing to do in the agenda is to work out the example of what this is. All right, because I think the calculation here would be something for you to see. And so we work out the examples and show you how to compute this. Okay. And then the next thing is to explain why it's true. So examples. Okay, how to compute camera bound, which is a very basic skills. So for that, right, let us do concrete examples. Let's say exponential lambda. Okay. So again, notice, right, the camera bound. So okay, let me do this, right? How to compute example, I guess. Computing camera. So notice that the camera bound does not depend on how theta hat is constructed. So in all my example here, I do not even have to tell you what lambda hat is. All right. We will implicitly kind of remember, for example, here, the lambda hat is x bar, but we do not need to if you just want to compute camera bound. Okay. So what does camera bound require? So remember, camera bound is, so the quantity to compute, okay, the quantity to compute is expectation of the derivative with respect to theta, whatever that is, of the density or the probability distribution. Sorry, there's a lot. Square. Maybe I forgot to put a lot. Oh yeah, there's a lot. Good. Okay, like this. By the way, this has a very special name. This is called the Fisher information. Okay. The textbook does not mention this as a specific quantity, but trust me, if you do any statistics, more advanced or even in other courses, you will hear of Fisher information. So this is the Fisher information in this case. All right. So in a sense, and we can give it a name, okay, I of theta. So in a sense, the camera bound can be compactly written as 1 over n I theta. Okay, so so the object to be computed is this. After that, you just do that. So all right, so in this example, what is the Fisher information? Well, so first you need to have the density, right? You need to have density. So the density, right, is clear. It is, let me do this, f of x lambda, right? Here theta is lambda, is 1 over lambda eta minus x over lambda. All right. So here is where the notation matters. Remember when I said big X, right, in this class means random variable. So exactly, right, this is where it matters. This is big X, right? This is small x, because here it's meant to be a number, right? A point, a value of your density. Here, what it says is basically the idea is you substitute big X in where you see small x. What big X do you substitute in? The big X that has the same distribution as the population. Okay. So in other words, this right here is a random object. And you're supposed to take the log, differentiate, square, and take expectation. Okay. Sounds like a lot of things, but trust me, it actually simplifies things a lot. So, all right, is it okay? So I guess the biggest thing to remember is that this right here is to take the population distribution, random variable x, to plug in where you see small x, okay? So again, so big X right here, let me emphasize, is an exponential lambda. That's the point. You plug the random variable into its distribution, okay? All right, so next we take the log. Right? And next we differentiate. Right? Then we square it. Sorry, log. So x squared over lambda to the fourth minus 2x over lambda cubed plus 1 over lambda squared. Okay. Then we take expectation of this guy. Take expectation of this guy. Okay. Expectation. So the Fisher information, right? I of lambda in this case, which is expectation of, this whole quantity, will be, well, what is expectation of x squared? X is exponential lambda, right? So variance of x is lambda squared. So expectation of x squared is 2 lambda squared, right? Because expectation is square plus the square expectation. Expectation of x is, of course, lambda. And this is 1 over lambda squared. Is it okay? So obviously everything reduced to 1 over lambda squared. Any question? So the bound, right? Is 1 over n times the Fisher information, which is lambda squared over n. What this means is any lambda hat who is unbiased will satisfy its variance is higher than this, or at least this. Okay. That's for the exponential population. This is universal. This is universal for the exponential population. Okay. So in a way, you can say that the bound is a population property, is independent of how you estimate. I mean, it's a sample property in the sense that it depends on sample size. But beyond that, right, it doesn't care how you compute the lambda hat. Question? Okay. So Do we know any lambda hat that has this variance in this case? Correct. If lambda hat is equal to x bar, then x bar is obviously unbiased for lambda, right? You want to check this, all right? Because again, Khmer Rao in this form that we're stating it is only available, or is only right for unbiased estimator. And variance, right? X bar is sigma square over n, which is lambda square over n. Exactly here. So you see, then we can conclude that X bar is the UMV in the exponential lambda. So in other words, when we use X bar as an estimate for lambda, in some way we are doing something optimal. We have achieved the smallest variance possible. Any question? Okay, so let's do something discrete. Let's suppose you have x1 up to xn, IID, Bernoulli, P. All right. Then again, right, remember the Fisher information is this. So here, right, we're dealing with f of x and p. P is our unknown parameter. What is it? Well, if it's a Bernoulli, remember, if it's a Bernoulli, it only take on, be careful here, Ramadaf, like it is not a binomial. The textbook would, like I said, would group the whole thing in here into a binomial NP. All right, so in that sense, this x and that x that I'm talking about are different x's. So by their x, the textbook x, what they talk about is they talk about the whole sample. Okay, you understand, right? Because the sample is one, let's say 1, 1, 0, 0, 1, 0, 1, right? So you can view this as a binomial what? 3, 6, 7, right? With you know, x equals to 4. Okay, that's the text. My point of view is I still want to preserve the trial kind of formulation. So I would call this x1, x2 up to x7. All right. And so my single x is any one of these guys. This is a population distribution. Okay, not this. Yeah, it somehow is similar, but if you do this, then you won't have the individual trials. All right, I don't care which way you do it if you understand, but the x in the textbook is the sum of the xi for me. All right, but like I explained before, I do not like this approach because somehow it takes the whole sample away and you just sum it up into one single random variable, which is fine. It still makes sense, but I want to preserve, you know, the x1 to xn kind of approach like this. All right. So because of this, my f of xp will be this. x to the p, 1 minus x to the 1 minus p. Okay? And try to understand, right? Because this is what is it saying? Is equal to oh, sorry. Am I right? No, the other way, sorry. P to the x. 1 minus p to 1 minus x, sorry. Yeah, okay, right? So that means it's equal to p if x is equal to 1 and 1 minus p if x is equal to 0. That's this, right? Okay. Why? Because I will have to take the log of this, square it, and take expectation, derivative and expectation. Okay. So this is the fxp for the Bernoulli p. Any question? Okay. So now we'll take the log. I will differentiate. Okay. And then I will square it. Okay. And then we'll take expectation, which is the Fisher information, depending on P. All right. So, moment of truth. What is expectation of x squared here for Bernoulli, right? So let's not forget what are we doing. It's very helpful, right, to write down more than you need. What is x here? X here will be a Bernoulli p, right? Because that's the population distribution I'm quoting from, right? Bernoulli p. Same as the other one was exponential lambda. Okay. So x is Bernoulli p. What is expectation of x squared? What's the variance of Bernoulli? Correct, exactly. So p1 minus p plus p squared, very good. What about this right here? What about 1 minus x squared? What is its expectation? I'm saying this, right, because you see, I understand that a student who do not see what's going on, when they come to here, they'll just panic. They will be like, what is this calculation? How can I even do it? Okay. The thing is, you have to always get a handle on what it is that you're looking at. So this, we got it, right, without any computation because we know the variance of Bernoulli. What about this? Yeah, I think I'm looking for something a little bit more slick than that. How about this? 1 minus x is also a Bernoulli, isn't it? It's Bernoulli with what success probability. Exactly. So by what Young Yu just said, what is the answer here then? Okay, so I hope you appreciate the point of view that will allow you to not do computation, right? If you have to do computation at every step, you will get super tired and confused. Is it okay? What about this term? Well, here, I guess there's nothing slick here. It's x minus x squared, right? It's x minus x squared. So that would be expectation of x minus expectation of x squared, right? Which is p minus, what we just say here, p1 minus p plus p squared, which is zero. So it's just these two terms. Are we okay? Let's simplify even more, right? That's not the end of the story yet. Let's simplify more. Yeah, Christine, so I'm doing the mixed terms, right? I'm doing the cross terms. The cross terms, I'm not looking at it as a random variable. I mean, it is a random variable, but what can I do? I just look at it. Now this is where, like, expectation rules helps, because I just look at it as x minus x squared, right? I just look at it x minus x squared. And x, right, has expectation p. X squared has this expectation, as we just said. And notice that this is minus p squared plus p squared cancel, p minus p cancel. So are we okay? Any question? Christine, you're fine? If not, let me know. Any step that's still unclear? Okay. So let's simplify the information even more, right? Because you see, that would be, right, 1 minus p over p plus 1 plus p over 1 minus p plus 1, right? Well, what is this? Let me see here. This would be, right? So 1 minus p squared plus p squared divided by sorry, no, I don't want to do this. Let me show you. Okay, so here, right, I cancel this to give 1 minus p over p. This is 1. Cancel this gives me p over 1 minus p. This is 1. All right. Next thing I'll do is this. This is 1 over p minus 1, right? Like this. I will combine this, actually. All right, I'll combine this to give me, right, this is p plus 1 minus p, right, divided by 1 minus p. So I will get 1 over P plus 1 over 1 minus P. Okay, which is just 1 over P1 minus P. No, Christine, very good. I did not, because here, right, is 1 over P. This gives me a minus 1. So this minus 1 with this plus 1 cancel each other out. And this plus 1, this combined to this. No, don't worry, right? I will tell you that if you feel this computation is a bit, I don't know, right, a mistake inducing, you're fine, right? I will show you an easier way to do it, but first I want to show you the orthodox way. Well, not orthodox, but second, let me tell you, right? I have a guiding principle, right? Besides trying to keep my head clear. Do you see why that I know that I should get something like this? Or at least this is something that I know I expect should cancel to, should simplify to. Do you recognize why? This is something that I would intuitively lead toward. Of course, not must, but I think my computation should lead to something simple. You know why? Because the Camara bound is, right, 1 over n efficient information. And when we look at this, what kind of p hat do we have in mind? What kind of p hat do we have in mind? For example, right, in this population, what do you think p hat is? Sorry, not population, this sample. What do you think p hat is? 4 over 7, right? So p hat, the p hat that we have in mind is x bar. Still, right? What is variance of p hat in this case? And so because of this, and I knew that the Camara bound must somehow circulate around something like this. That's why I knew that even though I get this kind of ugly thing for the information, it should simplify down to something simple. And that's why I keep looking for ways to simplify it. Is that okay? But that's experience. But I'm telling you this as a guiding principle for when you do a problem, you should kind of have an expectation of what it may lead to. I know that the information should lead to something that kind of mimic the structure of the variance, because I think I expect the X bar to be it. So that's why I keep simplifying, right? I don't look at this and I say I stop. Any question? But right, so incidentally, exactly this shows me that the X bar here, right, achieves the bound. Right? X bar here achieves the bound. So therefore, here in this case, X bar, right, P hat is the UMV for P in the Bernoulli family. Any questions? All right. So if throughout this computation, right, I show you the orthodox way. So if throughout this computation, right, you feel that the computation is a little bit hairy, you're right? So in other words, computing the information, which is expectation of the partial of the log. Okay, is a bit tedious, okay, due to the square. If you pay attention, right, up to here, it seems fine. But exactly when you square things, right, things get mixed up. And that's where we have to drag in the variance in all these terms. Same thing here. You see up to here is fine. And actually the computation not too bad, but you see we drag in the square terms and we got, the product. So here's the shortcut, and I'll explain. The Fisher information has another formulation. We can show that the Fisher information is minus the expectation of the second derivative. Okay. Notice there's no square here. No square here. So this will allow, and differentiate it will potentially make it even simpler. So this will allow you to do the computation of the Cramér round much easier. This is the way it's stated, but this is the way to do computation. All right, and we'll see that, we'll show you that it's equivalent. So let's revisit the two examples we did. Remember, what was the Fisher information in this case? One over lambda squared. All right. So let's pick up right from here. Right. This is the derivative. Right. This is the derivative, the first derivative. So the first derivative is minus 1 over lambda plus x over lambda squared. Okay. So instead of now squaring this guy and take expectation, the other way, the alternative tells me to just differentiate one more time. So if I differentiate one more time, I will get 1 over lambda squared, right, minus x over lambda cubed. Sorry, minus 2x, right, over lambda cubed. And then I just take expectation of this. Expectation of this is 1 over lambda squared minus, what's expectation of x? Lambda, so 2 lambda over lambda cubed, giving me minus 1 over lambda squared. Should I be worried that I get something negative? I should not, because here exactly there's a negative out front. So therefore, right, if you do the alternative, it tells you the Fisher information is 1 over lambda squared, which is exactly what we got before. Notice how it's much faster than the other way we did it. Question? Let's try the other example. Let's try the Bernoulli. Okay. So the Bernoulli, right, up to here is fine, right? When we square it, it gets hairy. So let's take this, right? Let's take this. So x over p minus 1 minus x over 1 minus p. Let's not forget, right? We got the Fisher information to be 1 over p 1 minus p. So instead of squaring this now, like we did and take expectation, we'll just differentiate this guy one more time and take expectation. Differentiate this one more time, give me 2 minuses. So I got this like that, right? 1 minus comes from the power and 1 from the minus in front of the p, the chain rule. Okay, so now I just have to take expectation of this. So remember, right, x here is Bernoulli p. So this is minus p over p squared. And this will be 1 minus p. Which you see is just minus of 1 over p plus 1 over 1 minus p, which is minus 1 over p 1 minus p. And so of course then, right, because the Fisher information is minus of this, we got the same answer. Are we okay? So, right, even though the textbook posts this, computationally, this is much easier to work with. Any question? All right. So we have time for one more example. I can do either a Poisson, which is discrete, or normal, which is continuous for mu. Which one do you want? Poisson? Normal. Okay, cool. All right, so let's do x1 up to xn, IID normal mu sigma square. So actually, it's interesting here in a way. The normal actually has how many parameters? It has 2. So actually, how many bounds can we come up with? We can come up with 2 bounds, one for mu, one for sigma square. All right, let's see how they do. So first, right, the density function is just this. Right. So take the log. Forget the 2 pi, right? Because we'll differentiate anyway, so it will disappear. It'll be, sorry, it'll be C, right? And then plus, rather minus, right? 1/2 natural log of sigma square minus x minus mu square over sigma square. Okay. So this is the object we'll work with. We will do bound for mu and bound for sigma square. If it's bound for mu, is even easier. We don't have to care for this, right? We just have to differentiate this guy twice. The first derivative will be 2x minus mu over sigma square, right? The second derivative will give you, oh, I have a wonderful habit of dropping constants. No 2, right? Just this. The second derivative is just minus 1 over sigma square. See how beautiful it is? So even how easy it is. So the chimeral bound for, so the Fisher information for mu is 1 over sigma square. The bound is 1 over sigma square of n. Do we know any unbiased estimator that achieves this for mu? X bar, right? Any question? So let's do bound for sigma square. So we differentiate this guy with respect to sigma square, right? So first derivative, remember, right, with respect to sigma square, not sigma. So I get minus 1 over 2 sigma square, and then plus x minus mu square over 2 sigma to a fourth. Is that okay? That's the first derivative. The second derivative is awkward now. Let me do this, all right? It's just because, you know, I know sigma square is something square, but here, right, we want to take sigma square as a single constant, okay? Is, what would that be now, right? 1 over 2 sigma to a fourth. And then this is sigma square square, right? Let's do this because so you bring the minus 2 out and raise it to a third power. So that we minus x minus mu square over sigma to a 6. Oh, my 6 is now awkward. It's like sigma, like that. Is that okay? So the expectation of this, which is the Fisher information for sigma square, right? One over 2 sigma to a fourth. Expectation of this, oh, apologize, right? I should keep big X because I want the randomness. It doesn't matter here because it disappears anyway, right? Big X. Well, of course, right? X is a normal mu sigma square. Okay, X is a normal mu sigma square. So because X is normal mu sigma square, expectation here would be sigma square. Which is minus 1/2 sigma to a fourth. Right? So what's the Camara bound for sigma squared? 2 sigma to a fourth divided by n. Do we know any estimator that achieves this? Do we know any estimator that achieves this? Okay. So yeah, right? First, does S squared achieve this? What's the variance of S squared? Right. So exactly, right? S squared, very good, is bigger than this. Notice, right? Exactly, you see, this is where first time, right? I think the other cases you're probably just disappointed. You're like, okay, always true, true, true. What's the point? Right? You see here, you see that exactly the first time you see that the Camara bound is not. Well, we'll get there, right? But let's get to right. It's not achieved. But does S prime square achieve this? So variance of S prime square is 2 sigma fourth over n. Okay, look back into our discussion. Okay, so yeah, I think Madhav was very excited about looking at this. So is S prime UMV the UMV? So is S prime square a UMV then? Exactly, that's a trick question. Unfortunately, is biased, so somehow is excluded from this consideration. Well, so then does it then, right? Is S squared the UMVE? Right, strictly speaking, you have to say I don't know with this evidence, but yes, I believe so. All right, I do believe so. I don't think you can do better than this for unbiased. But you see, now it's difficult. How do you know this is the UMV? So just right here, two answers. A strict answer is I don't know. I haven't thought about it carefully. Feeling wise, experience wise, I think yes, but I have no rigorous backup. All right, so that's the answer. Is that okay? But yeah, S prime is not the UMV. And then right, you see the fight between these guys, if you care about that kind of 1/n thing, then you have to really combine their MSE to compare them, right? Mean square error. Any question? All right. So I think it's a good place to stop right now. Next time, right? Proof of chimera. Why it works, how it works, and then exceptions. Where it doesn't work. Actually, notice in all these examples, I was very careful to avoid one very popular family, okay? And you may wonder why, all right? So, but that's for next time, because I just want to end the class a little bit early. So if you have any question about anything, I can answer your question, all right? So Friday, right, I won't see you because the exam is on lockdown browser. But if there's any issue, exit it, shoot me an email. I will be on email. And well, I'll be on Zoom, right? If you want to jump on Zoom to talk to me, feel free. If not, shoot me an email. I will answer, try to troubleshoot your problem, okay? Worst case, if you cannot get functioning, just go ahead and do the exam, all right, and submit it. I will arrange, according to how I see fit, an oral component to check to make sure that you're the author of your exam. Okay, but if you have already written an exam, at least the bulk of your scores or whatever, provided that I can trust, right, that you wrote it, then the oral component, just like, to make sure that you did what you did, right? So in any event, right, if you cannot get it functioning, just go ahead and do the exam as usual, and we'll do something extra. But if you have, your proof that you were doing the exam, with the lockdown browser and with the webcam on, then your grade is your grade, no question asked. All right. So yeah, that's that. I will do the list that you requested me to do. Any remaining questions, I will try to address. Thank you. Thank you. You too. Thank you. Thank you. You too.